on and some possible application. Okay, so let's start in this lecture. First, I will talk about evolution of smart grids. Then we'll talk about smart grid architecture, its conceptual model, technical model. Then we'll discuss also some important topics which are very integrated part of future smart grids, that is substation automation using IISc 61850, and a recent work which uh, we continuously working on, that is a new concept called data markets for smart grids. So let's start on the evolution of smart grids. So we know the traditional power grids basically was a hierarchical system, right? It has three distinct entities. One was power generation, mostly from coal, and there are some hydro and nuclear also. And then you had your transmission grid. Your generating stations were mostly far from your load center, which is distribution system. So to bring the power from generating station to your home, we had transmission grid, and then near the load center, the voltage will be stepped down, and the power will be distributed to various entities like industrial users, commercial users, and residential users using distribution line. Okay. So if we look at the problem, so this was mostly like one way pipeline, we can say, like source did not have real time information what is going on in distribution system, right? So there was communication, if it is there, it was mostly one way, and all mostly at the transmission level. Okay. And often the grid was over engineered. So it was basically designed very much pessimistically, because previously all utilities were state owned. So competition, market, this was not there. So there was no pressure to be uh, efficient. There was, so that's why often the grid was over engineered, like your transmission lines, they were underutilized. Okay. So economically, it was not a very efficient system, and also the increase in demand and was did not match the growth in infrastructure, right? So this particular example, if you see, in 2003 the blackout happened in US, right? We know US as a very advanced country, but even in that country the electric infrastructure was very outdated, even though they progressed in computing technologies, electronics, but somehow the electric infrastructure remained in the old era. As a result, they faced the blackout, right? So this is also a problem in traditional power grid across the world, that there is a lack of growth. There was a lack of growth in infrastructure. So that has often led to system stability issues, blackout. Okay. So again, so what I just said, that unforeseen surge. So if you are not monitoring well, if you are not planning well, then unforeseen surge in demand may lead to catastrophic blackout. Actually, in Texas last year, so there was a huge blackout for multiple days, right? That happened due to unforeseen demand rise. Okay. So this is even still a challenge for traditional power systems. Now, to find a solution. So the goal was to better monitor the system, identify the problem, solve it, use more technologies like use computing technologies to protect the grid infrastructure. So for better monitoring, the utility started adopting SCADA, and then currently we have this PMU based wide area measurement system. So the journey is is to become more better monitoring, better control. Okay. So utilities are now installing more better SCADA, which can monitor the system at higher rate, higher frequency, or higher sampling rate. Yeah. But distribution system, to some extent, remained outside real-time control. So now, but if you look at that, 90% of all power outages happen actually distribution systems, right? So there was a effort to modernize the distribution system in order to modernize grid, because one of the most inefficient portion of power system was distribution system. It has huge losses, right? Lot of losses used to happen. So the people realize that if you want to modernize the grid for better monitoring control, you actually have to modernize the distribution system heavily. Okay. So due to the rapid increase in cost of fossil fuels and inability of utility to expand generation capacity with rising demand. Okay. So due to these two constraints, the utilities focused more on the demand side management, right? Because you cannot increase generation as you want, right? It is constrained by economics, fuel cost, and many things. So one way is to have better management of distribution system, better control over demand. Okay, reduction of loss. So this was another approach that utilities took. And at the meantime, when computing technologies were developing, right? So slowly from electromechanical devices such as electromechanical meters, we started to advance automated meter reading system, right? Because when you have digital technologies, you can have digital devices for reading your meter, right? And with communication, uh, better communication channel. Okay. So automatic meter reading is actually, okay. So this last line should be automated AMR systems allow the transition to the smart grid. Okay, that do not should not be there. So, using the AMR system, utilities can read the consumption records, alarms, and status for customer premises remotely, right? So, utility has better information, right? So, currently, this automated meter reading is basically restricted to the reading of the meter. Okay. However, it does not let utilities take corrective action based on information received from the meters. Okay. So from automated meter reading, then came the advanced metering infrastructure. Okay. So it is not about just reading the meter. It is also about how utilities can control the demand. Okay. So that's why it came up with two-way communication system. Okay. So AMI system is basically backbone of smart grids. So from AMR we move to AMI. Okay. So advanced infrastructure is the backbone with two-way communication channel which allow the demand side management is the backbone of smart grids. Okay. So now we hear often this word smart grids. Often people debate the use of smart grid. People say that, okay, what is special about it? It was you just have some communication, right? So what is that smart grid? So if you go by the definition of NIST, NIST means National Institute of Standards and Technology by US. So it says that so NIST is basically to was formed to coordinate the research and development of a framework to achieve interoperability of grid system and devices. Okay. However, a precise and comprehensive definition of smart grid has not been proposed yet. But if you look at the smart grid, what are the features? So now if we look at the use of word smart, suppose when we say that, oh, in this student is very smart, like this this boy is very smart. So what actually we mean that? So he that means that person is basically intelligent, right? He can he can think, he can do complex calculations in their brain. He can understand what is going on around him better, right? And then he can take a better decision, right? Either he can solve a complex problem or he can take better decision in his life in every way, right? So the if we use the use of smart in our life, the same way the smart word is applicable to grid also, right? So so then smart grid basically means a grid which has better awareness what is going on around it or inside it, right? Then it can take a better decision to maintain or operate the grid, right? Better control basically, right? And also it has better management from the point of view economics, costing point of view, right? So this is some idea of like what we can say abstract meaning of smart grid, right? So if we can relate it the way we use smart word in our daily life, we'll get some idea of what smart grid is, right? Now if you look at some of the characteristics of smart grids, so first is self-healing. So if there is a disturbance event, how your grid can self-heal, right? Then active participation by consumer in demand response, right? So demand was not related with your generation scenarios, right? So now demand is also uh, like the consumer can respond and change your the demand curve appropriately, right? Then it should have resilient against both physical and cyber attack. This has becoming a very important thing now. So it should have good amount of resiliency against attacks. Then provide quality of power. Like quality means it there should not be much load shedding, which is very common even today. So there will be uninterrupted power supply with good quality, like pure sinusoids, not much distortion. Okay, so that should be there because our life is increasingly becoming dependent on electricity, right? So in future smart grid, the continuation or the power should be uninterrupted, right? Then you should have all generation and storage options, different type of generations like renewables, right? All type of renewable energy you should be able to use more, and then similarly storage, appropriately use of storage mediums. Okay. Then smart grid should enable new product, services, markets, right? New type of developments, the product development should happen. Okay. Then another aspect is the economic aspect, right? So the asset utilization, whatever asset utilities have, it should be very efficient. Like if you have a distribution line, if you have transmission lines, they should be efficiently utilized, right? So that means those lines should be operated very closer to the limits. If you have power plant, so your plant factor, load factors, so those should be high. So to realize this new paradigm shift, NIST provided a conceptual model. Okay, this is a conceptually what they said. So they divided the smart grid into seven domains. So here you can see generation, bulk generation, transmission, distribution, and then customer. Then you have markets, operations, and service provider. Now, if we look at what they are, so consumers basically the end users of electricity. They sometimes may also generate using rooftop solar, wind, okay, store and manage the use of energies. But basically, they are mainly the consumers of electricity. Then markets, so markets where buyers and sellers they trade electricity and also the ancillary services. So service providers are basically organizations who provide services to electrical consumers and utilities. Then you have operations, mostly the managers of the movement of electricity. Like we have this SLDC, right? State Load Dispatch Center. Then you have regional load dispatch centers such as SRLDC, NELDC. Then you have national load dispatch centers, right? They are basically the operators. They ensure the reliable operation of power grid, right? They are basically managers of the movement of electricity. Okay. Then you have bulk generators, so generators of electricity in bulk quantity. So previously it was mostly the coal-based power plants, but now we are also having bulk renewable power plants, right? Like Pavagara in Karnataka will be having around 2000 megawatt solar plant, right? So now India is having many big solar plants, at least 500, 600 megawatt operational. Okay. So that is bulk generation. And then you have the carriers of bulk electricity over long distance. So this is your transmission network. Okay. And then you have distribution system. So distribution system basically they are the distributors of electricity to consumers. And sometimes if you allow consumer to inject power into the distribution system, in that case distribution system will also carry power from consumers to another consumer. Okay. So in this figure you can see that there are various relations are uh, modeled here and shown in this figure. So if we look at the technical models, so smart grid mostly has three aspects. One is infrastructure, management, and protection. So smart infrastructure system, so it contains three subsystems. One is smart energy subsystem, smart information subsystem, and smart communication systems subsystem, right? So smart energy subsystem. So now, especially in the distribution system, right, we have introduced the generation such as PV, wind, right? So now your distribution system will have also bidirectional flow of electricity, right? Which was different from the conventional distribution system. So this is one thing is happening in generation scenario. So the concept of virtual power plant has also been introduced. What is virtual power plant? It is nothing but a group of small scale power power generation unit in the distribution system, right? Which you can control to behave like a big power plant, like virtual power plant, right? Using your better communication system. So it's nothing but a small power plants which you are operating coherently and which may appear as if a big power plant. So this is basically the concept of virtual power plant has been introduced. Another thing is happening is basically the renewable energy integration, right? So India especially is going for large scale renewable power plant, right? As I said, Pavagara in Karnataka is expected to have a 2000 megawatt solar plant. Similarly, in Gujarat, Rajasthan, lot of big power plant are coming based on PV, right? So in future, we will see lot of like the generation scenario will change completely. So instead of coal power plants, we'll have lot of renewable based power plants in the future. Now, obviously, this renewable integration is a new paradigm, right? So that this transition from coal to renewable is faced actually a lot of challenges and still facing. But we have overcome lot of these challenges. That's why you can see lot of big renewable based power plants are coming in India. But if we see what are the technical challenges like power system planning, the intermittency of renewable is a big issue, right? Because previously in thermal power plant you can control how much coal you will give input, how much steam you will generate. You had control. So the uncertainty in load was managed by controlling the generation. But in case of renewable, you don't have that control. So here the challenge is your load is uncontrollable, is kind of uncertain. Your generation is also kind of uncertain. So in that case, maintaining load generation balance in power system and planning is a big issue. Okay. Similarly, due to the intermittent nature of renewables, the concept of generation prediction has come. Right. Now, previously we used to forecast load, but now we also have to forecast generation. Right. So to handle this intermittency, now energy storage usage is being looked at. Like government of India is looking for large scale grid scale energy storage devices, right? Which can take care of uncertainty in generation, right? And maintaining reliability, security is another technical challenge in the renewable area. Similarly, at the beginning, financial was also a big issue, right? Because these renewables are very costly. Those technologies are very costly, right? So how to fund those projects, from where the money will come, how the recovery in the investment will happen. So there are huge financial challenge at the beginning. But now things are much better. Now the financial model has been established. So to some extent, now things are much better than how it was. Okay. So another challenge is societal, like how we can bring consumers into the demand management. So in Europe, USA, or North America, the demand side management is comparatively better. But in India, we are still in the nascent stage. This is about involving the consumers into demand management. Okay. So now to solve these technical challenges, so there are many solutions are being proposed. Like in generation, you can see smart inverters, forecasting, accurate forecasting, virtual power plants in distribution systems. Then better control for renewables. So initially, when PV came into picture or wind, so the grid operators did not expect them to behave as a synchronous generator, right? But now they are putting criteria that you should have LVRT capability like a synchronous generator, right? So they are putting lot of criteria on this or expectations from these renewables, right? Then also they are thinking about this reserve capacity. From network point of view, obviously we need to expand grid, high voltage AC/DC lines, distribution automation. They are trying to find what is the dynamic line rating, synchrophasers, more interconnections being established, then fax devices. And then demand side, you have, I think this particular block is just wrong. Yeah, so demand side basically you have demand side management mostly, right? So various kind of demand load control technologies are being proposed. Better monitoring such as micro PMUs are being installed in distribution systems, right? Better in India, better theft detection. That is a big challenge, right? Loss reduction, how we can reduce loss in distribution system using technology. So those things are happening in the demand area or distribution system. Then storage. So due to this intermittent nature of generators, now we are looking for good storage devices, right? So apart from pumped storage hydro, then we have CHP. So CHP in India is not there much, but it is combined heat and power. This is mostly in Europe, right, where they use heat a lot due to the cold weather. Okay. So storage system, if we see that we have mechanical storage system, pumped hydro, compressed air, flywheel. In electrical, we have supercapacitor, superconducting magnetic coil. Now electromechanical, we have batteries which we are familiar, lead acid battery, nickel cadmium, lithium oil. Then high temperature batteries, sodium sulfur, Jubila, flow batteries, redox batteries basically. So these, but redox batteries and high temperature batteries, these are not much in use. Mostly the commonly used battery technology is lead acid, but now lithium ion is also getting because it is much better technology than lead acid. So now lot of funding is coming to develop better lithium ion technology, and in future batteries will be mostly lithium ion based batteries. Then in thermal storage we have salt, and then we have obviously solar. Yeah. And in chemical, that is also another area where uh, from environment perspective it has lot of prospect for future. One such is hydrogen fuel cell. So this is getting very intense research interest. Recently, this month only there was first conference on hydrogen based uh, hydrogen for hydrogen economy. It was organized by CBIP Delhi. Okay. So now what is the typical big energy storage application and different voltage levels? Like peak shaving is one thing, load leveling, voltage support, then you have capacity farming, then spinning reserve, load leveling, frequency regulations. These are the possible applications of energy storage devices at various basically level. Okay. Now, one thing I would like to focus here on, which is very new, I thought may not be much familiar. This is hydrogen application of hydrogen into power systems, like hydrogen as a fuel in power system. So this is getting increasing attention from all over the world. Europe is extensively working on hydrogen energy systems, right? So why? Because if you generate hydrogen, if you use hydrogen as fuel, then using electrolysis process, then your byproduct is water, right? And hydrogen is abundantly found in nature. It is everywhere. So currently, countries like India heavily depend on outside, right, for fuel because we import oil a lot, right? So our dependency on foreign countries will reduce if you start to use hydrogen as energy carrier, right? And also it is environment friendly, right? So that's why this is one of the very what are getting lot of attention, and Europe is already doing lot of research in hydrogen. Okay, so now if we look at, this is what we call renewable hydrogen power system. Now what is renewable hydrogen? See, hydrogen can be produced in many ways. The existing way of hydrogen production basically leads to carbon dioxide gases, so they are not environment friendly. But there is, if you generate hydrogen by electrolysis approach, then that process is environment friendly. So the concept is, in future, because we have the intermittent sources which we cannot store, right? Wind, solar. So what you do is, using wind and solar energy, you do a electrolysis process and then you hydrogen. So that means you basically convert your intermittent energy sources through electrolysis process into hydrogen. Now hydrogen advantage is you can store it for longer duration, which is its life is very long. So you keep it stored, and whenever you require electricity, you convert it back to electricity via fuel cell. Right. So this is a block diagram. So here you can see, using external energy sources, which would be wind and solar, you do electrolysis and generate hydrogen. That hydrogen you store, and whenever you require, you using fuel cell, you convert this back to electricity. So this is called renewable hydrogen because this process is free from greenhouse gas emission, or it is the greenhouse gas emission is very low in this approach. So this is called green hydrogen or renewable hydrogen. So there are lot of projects are being launched mostly in Europe. So this is called project data zero. So they used hydrogen for long term and medium term energy storage. This is basically a data center. So this data center is free from coal-based power plant. Like it does not use any energy coming from coal-based or any other pollutant. Right. So here you can see that this data center mostly run by PV panels. It has wind turbines, right? Now, as you know that in the night PV will not be there, right? And also there will be variation in the seasons, right? There are seasonal variations in these sources. So to take care of this intermittency, what they do is they use hydrogen for medium to take care medium to long term variation. Okay. And they are using batteries and supercapacitor for very short term variation in generation, right? So here you can see that they have a common DC bus. So whatever energy gets generated using fuels electrolyzer, they store it as hydrogen, and whenever is required, mostly medium and long term, they convert this hydrogen back to electricity and supply the loads. Okay, so this is in a real data center. They are running like this. So this demonstrate that this kind of architecture actually is very much feasible. Thank you. Similarly, there is another project going on Europe that is called Project Helios. So here what they do is they have a 45 megawatt wind farm. So what they do is they currently have a 2.5 megawatt electrolyzer. So rest of the electricity they are pumping to utility, and they are using a 2.5 megawatt electrolyzer to convert the wind energy into hydrogen. Now this hydrogen partly they send it to the consumers of hydrogen. They can be industrial consumers and gas. Basically they inject into gas network. So this is called power to gas. Okay, they generate gas from renewables and they use that gas for consumers who need these gases, and a portion of this hydrogen they again convert back to electricity whenever is required. Okay, so in this demonstration project they have a fuel cell of 100 kilowatt. Okay, so after successful running of this project, they want to expand this model further. Okay. So this shows that we are working towards a hydrogen-based energy system in future. And this is especially again the advantage is you can take care of the intermittency in wind and solar easily, because hydrogen you can store for longer duration easily. Okay, so this we expect to see in future more and more. Now smart energy subsystems, so also we have these DGs in distribution network. Okay, and now we are also looking for DC based distribution system, right? Because now people see that all your solar panels they generate DC. So now people are thinking why to convert this DC to AC and again from AC to DC, because again your CFL bulbs and all those new generation loads actually work on DC. So they are thinking why you convert so many times. Instead, why don't we go for DC distribution system? So this is also another thing is developing, that DC distribution is again getting kind of attention. Okay. Then we are also thinking about energy internet, right? The way internet works, right? Your router sends the data packet to a particular destination, but we know that we cannot usually send energy like that, right? In the conventional system. But now they are talking about this energy internet where you will have kind of power router concept. So there will be one device which will send power in a particular line, basically using power electronics technology, where you can have better control in power flow. So smart in the transmission grid, you are having smart control centers, like more analytical use, more better visualization, use of synchrophasers, like time synchronized measurements, right? These are happening in the transmission level. Our control centers are becoming more uh, advanced in terms of digital technology, right? Then substations are also becoming smart. So what we mean is smart is digitizations is happening, like IISc 650, right? more digital technologies are being used. This is helping to reduce the size of the substation and also use of copper cable to reduce the cost, right? So here comes the role of IC 6150, right? So this is basically a standard for substation communication system mostly, right? Now, if we look at the conventional substations, so how do we send? So in the field, you will have all these CTPTs, right? Which will step down the voltage and current from high values to low values. Now, how we send those step down values to control center, because most of your monitoring protection device will be in control center. So how do we step down, or how do we send this information? We basically use lot of copper cables, right? Currently, now another thing is happening in substation is previously we had electromechanical devices, right? So now with the advancement of digital technologies, now most of our monitoring and protection control devices, they are based on electronic technology or digital technology, right? Now we call them like intelligent electronic devices. Now from CTPT also there is evolution is happening, right? So previous current transformer, voltage transformer, they are being replaced by optical cities, right? Which are compact, which don't need oil, which don't have the problem of saturation, right? So in future, we may see more this kind of optical sensors rather than conventional CTPTs. So as I said that the field measurements were sent to control center via copper cables. Like if you go to any substation field, you will see lot of trenches, right? And huge amount of copper cables carry the your CTPT measurements to your relay panels, right? So these copper cables, first of all, very costly. It needs space, right? So here one major change has happened due to IC 61850. Right. So what is this IC 61850? This is basically the standard names IC 61850 communication networks and systems in substation. This is basically focuses on the communication within substation. Right. So the major problem of existing substation scheme is a large number of proprietary protocols and devices are used in substations. So often these devices they cannot talk to each other. That's why utility mostly give turnkey projects for substation. Like one substation is being built by a one particular company, and only their devices are used. This creates monopoly, right? And utility becomes totally dependent on that particular supplier, right? So that's why to break this monopoly, now utilities across the world they also want interoperable devices. A single manufacturer should not supply all relays, right, for a particular utility. So now due to all this uh, bottlenecks, like as I said, lot of copper wires, lack of interoperability, all these bottlenecks actually drive or has driven the development of this new standard, right, which tries to reduce the use of copper cabling in substation, which also looks at standardizing various functions in substation, which basically reduces the amount of copper cables, right? So As per this IC 61850, this is basically a communication standard. So it has divided a substation into three levels: process level, bay level, and station level. So one of the goal of this standard is to standardize everything so that the interoperability becomes easy. Because if everything is standardized, then every company has to use that standardized definition, right? Now, if every company is using a standard definition, standard name, standard function, then it will be easy for devices from two different companies to talk to each other, right? So this is one goal of IC 6150. So in that goal, what they have done is they have divided the substation into three zones, right? Process level, bay level, and station level. So process level is basically that portion of the substation field where your all current transformer, circuit breakers stay. So all individual circuit breaker, current transformer, voltage transformer, they form the process level. Now, bay level, what is bay? Bay can be basically a feeder, a portion or a portion of a transmission line, right? So, suppose whatever devices are connected to that particular feeder or that particular transmission line, they are grouped into a bay, right? Suppose at that line you have three CT, three VT, you have one transformer. So all these are grouped into a bay. We call it, this is a bay. So a bay contains several individual equipments. Right. Now at the station level, we have equipments or devices which looks at the whole substation together. Right. So again, so bay level is basically is a grouping of equipments together, right? So in bay level, you look at a group of equipments together, you control them together, kind of, right? You monitor them together. And station level, you look at the whole substation together. So substation level applications actually happen at station level. So what is process bus? This is nothing but the communication network which communicate between process level equipment and bay level equipment. Similarly, the station bus is basically bus which handles communication between bay level and station level. Bay level and station level. Okay. So here bus basically means communication bus, not the power system bus. This is a communication bus. Okay. So now if you focus on process level, actually in this level, the main change has happened. So in conventional substation, what we do is from CT and PT secondary, we take the copper cable which carries the analog signal. Take that cable to your substation control panel, right? So this whole cable carries basically your analog signal. Now, to reduce the amount of copper cabling, what the standard proposes that instead of bringing the copper cable to your control center and converting this copper cable's analog signal into digital, right? Instead of doing that, why don't you convert it in the field itself near CTVT? That means you do analog to digital conversion near your CTVT and you call it a merging unit. So this device, this new device, is called merging unit. So in merging unit takes analog signal from nearby CTVT and converts it into digital. The advantage is once you convert into digital, then you can club all digital signals into a Ethernet cable, and you take that Ethernet cable to your control center. So you can see that immediately we have reduced the amount of copper cabling, because from merging unit to your control room, substation control room, you do not need any copper cabling. You just need a one Ethernet cable. Right? So this has helped in reducing the size of your substation. Right? So this is a major change with respect to our conventional substation system. Right? So here you can see that from marching unit, there is a process bus. Again, this bus is basically a communication network. So through which your the digitized samples are sent to protection and control IEDs. Okay. Now, here you can see that from marching unit, you have communication, right? So to standardize this communication, IC 61850 has defined three types of packages or three types of messages. Okay. Goose is one message type, SMV is sample value, this is another message type, and MMS, this is another message type. So, what is Goose? Goose is nothing but a protocol to send the trip block information. The control signals are sent through goose messages. All tripping signal again should be sent as a goose message. And what will be the message? What will be the structure that is defined in this standard? Now, SMV is again a sample value. What is sample value? See, in your merging unit, you are converting analog signal to digital value, right? That means your sinusoid is becoming a sinusoid with digitized sample values, right? So these sample values are sent to your protection or control device via sample value message. So SMB protocol basically tells how to send this sample value message to protect other devices, right? And then MMS is nothing. So here you can see Goose and SMB are very time critical, right? Because Goose is related with the tripping of your circuit breaker, trip message, right? So it has to be sent in a specific time bound way. Similarly, sample values also basically a time bound message. Here, time delay should not be there. Fastness is more important, right? MMS is basically a protocol through which messages which are not time critical. As example, suppose you want to get disturbance information from a disturbance recorder. You want to access the historical data. So it is not that time critical, right? So in those cases, you use MMS protocol. So Goose and SMB protocols are comparatively is very fast, but it comes at the cost of lack of reliability, right? MMS is basically on the other way, it is very secure. It uses the 7 layer or 5 layer protocol, internet protocol, right? So in this simulation, I just show, just to give you a conceptually what happens. So marching unit converts the analog signals into digital, right? So all current and voltage values are converted into digital values, and then these values are sent to suppose a protection relay via SMV protocol. Okay. Now protection relay SMV is again sample value message. So using that protocol, the message digital samples are sent to relays. Now in relay, they based on those measurements, it calculates whether there is fault or not. If there is a fault, then that trip signal is sent to a intelligent control unit which basically controls the circuit breaker, and this trip information is sent via goose message. Once the circuit breaker is tripped, so the status of circuit breaker is again sent back to protection relay via goose message. And now in the station computer, it basically uses MMS protocol to know what is the status of the relay, and if it requires, it will send that information to other control center. So for that purpose, MMS signal is used, right? It can also issue the alarm. Now another thing is happening is under smart energy subsystem is microgrids, right? So we know that distribution system now can also have generators, but small scale generators, right? So now distribution system is a has all components of power grid, right? Now distribution system has load, it has distribution lines, and also it has generators. That's why it is a miniature version of smart power grid. That's why it is called microgrid, right? Now microgrid mostly can run in two operation mode, that is normal operation, where your main grid is also connected, and your DGs, distributed generation, they are generating power. So it is, we call it grid connected mode. Now, for some reason, if your grid is not there, then a microgrid should be able to operate in islanded mode also. That means your grid is not there, but using your local generation, you serve whatever load possible and you run in islanded mode. Okay. Then another thing is happening is electric vehicles. So you know, right? Due to these environmental concerns, we are shifting towards electric powered vehicles, right? So here we have grid to vehicle. That means your vehicle takes power from grid and it runs on that, and vehicle to grid. This is, if you require, you get the power back from vehicle to grid. So vehicle to grid interesting application can be a remote area, right? Remote villages. So where suppose when you power was there, you recharged your vehicle, right? So morning power was there, so you recharged your vehicle. Now maybe evening, night power is not there, and you are not using the vehicle, right? Suppose it can be a tractor which is used for agriculture purpose. So night, you can, when power is not there, you can get the power from your tractor back into your home for basic lighting purpose, light, other devices, very basic things. So vehicle to grid, especially in Indian context is applicable for remote areas, right? Where they face very frequent power cuts. So now we talk about smart information systems. So we are having now this smart metering infrastructure, right? Two-way communication channels, meters are coming, right? So now information is available in real time, so that the distributor system operator can take better decision and also the customer power demand can be managed in better ways. Similarly, we are having smart sensors. In addition to conventional CT and PT, we are having optical CTPTs. In addition, there are many other sensors like weather sensors are being used in power system, health monitoring, like transformer health monitoring. For that purpose, also new sensors are being generated, right? In addition, transmission level, we have phasor measurement unit, which is nothing but measurement device which gives time synchronized measurement, right? So information modeling management is also a key feature of smart grid because of use of these more and more sensors, digital devices, huge amount of data getting generated, right? So managing those data in a structured manner, you need modeling of data, and so for that, the data modeling has become a very important thing in smart grid. Then another thing is the analysis of this information which is getting generated, right? So huge data, you have to have the capability to analyze. Similarly, integration. So different devices are generating data at different rate, at different types, right? Suppose SCADA is generating 1 second. Your weather variables may be generated, weather sensors may be generating data in hours. And you have PMU which generates data in seconds, right? Multiple data. So how to integrate different data sources? So for that you need information integration framework. Okay. Then information optimization. So from large amount of data, how you can extract some meaningful information. Okay. So what you do is from large data, you remove some redundant or useless data, and then you optimize your data set so that you can use them in more efficient way. Another important aspect of smart grid is your wireless technologies. Okay, your communication systems, right? So previously in conventional distribution system, the use of communication network was very limited. But now, for better monitoring, we are having these wireless net technologies in distribution systems such as wireless mesh network, cellular communication systems, right? Then Zigbee is basically a communication which is a protocol which is designed for low data rate, long battery life application, right? So if your application like you don't have much power source, right? So you for your digital device you can use Zigbee communication, right? This is good for short distance communication, but problem is the data rate should be low, and advantage is long battery life, right? So this is another communication channel, communication protocol. Then you can use satellite communication, right? So this is if you don't have remote substations, you are basically can use the satellite communication because you do not have local communication infrastructure, right? So can we stop here for some time and then continue?
Yeah, certainly, yes.
Yeah.
Yeah.
So
So if you want to take some questions or you want a break,
Yeah, 5 minutes break. Then I will come back and I can
Okay,
take.
okay, 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 fine, it's fine. So we'll take 5 minutes break. So in between, if participants have say, any question, you can put in the chat box. That will be taken addressed later.
So any questions?
Yeah, so no technical questions in chat box. So yeah, maybe you can continue with the session.
Okay, fine.
Okay.
Okay. So we are discussing about the various communication technologies. So the wireless technologies, so satellite communications are suitable for remote places where you do not have the basic wired communication infrastructure. Right? For remote substations, it is popularly used. Then you have microwave communications like point to point communication. For that purpose, microwave used. Then fiber optic, this is becoming more popular, especially for high speed communication. This is especially needed for IC 61850 based substation. Because in IC 61850 substation, we are converting the analog signals into digital, right? That means in one cycle, we may have around 20 digital data, right? So to send them immediately once they are generated, you need very high speed communication network. So for that purpose, fiber optic communication is being considered. So in future, you can see lots of fiber optic communications in IC 61850 base substations. Then power line communication, to some extent, it has been used in power system for long. So and it will continue to use power sys- to be used in power system. In addition, what will come into picture in for future smart grid is broadband over power lines. Okay. So this is also being looked at that how you can provide broadband communication using your conductor wires. Then we come to smart management system. This management is basically managing your grid, managing your power systems. Okay. So the objective of this management is to energy efficiency and demand profile improvement. That means you basically it's a kind of demand management. You can do peak clipping if your demand curve has huge peak, then you can basically control your loads. You take some management tools, ways to reduce your demand peak. Right. Similarly, shifting of loads. If your load peak is appearing at a particular time which you don't want, you can do load shifting techniques to shift the loads at a different time. Then you can have strategic growth of load. Like you can plan your load growth in a strategic manner so that your infrastructure can meet your demand increase. Then you have valley filling. That means if your load curve has huge peak and huge valleys, right? So you can take steps to reduce those valleys. That means you try to increase your load value during this valley period. Okay. So you basically try to what you basically try to do is you try to achieve flat load curve. Right? Then you can have strategic conservation. That means you can reduce the load. Okay. And you can conserve in a strategic manner, in a planned fashion. And also you can have load shaping techniques like you try to shape the load behavior as per your requirement. Okay. So here another objective is to minimize the energy loss. Okay. So another is obviously you take management path to reduce the cost of utilities, because especially in India we know that most of our utilities run in loss, right? So here the cost optimization is very important. Another is price stabilization. So if you are participating in market, you have to ensure that electricity price does not fluctuate too much. Sometimes in some electricity market, the price actually goes negative. So which is not good. So price stabilization is also a management objective. That means through your market mechanism, through other mechanism, you basically try to ensure that the price of electricity varies within a band. Okay, so it stabilizes around an acceptable value. Then obviously due to this environmental or global warming, it has become very important that your emission is controlled, especially if you have coal-based power plant. Okay. Then those were the management objectives. Now, if you look at management methods and tools, so various optimization techniques are popularly being used to manage your power system, right? To operate it, starting from economic dispatch, right? Unit commitment. So there are various optimization techniques has been used. Now, in addition, the modern mathematics such as machine learning, game theory, from market point of view, game theory is very important. Right. So all these new techniques, new mathematical tools are being explored to manage your power grid. And the last dimension is protection. Right. So mostly two aspects. One is security and privacy, and another is system reliability and failure protection. So system reliability is basically ability of a component of a system to perform required function under stated conditions for a stated period of time. That means you are kind of expecting a particular performance always. Okay. Then you have distributed generations, right, which are widely used in smart grids. Okay. So, but these sources they are often intermittent in nature. Right? So you have to ensure the system reliability under this intermittent or variable nature of renewables. Okay. Then failure prediction and prevention. So failure prediction, because suppose a failure happens, whenever a failure happens, then you have to go and maintain it, right? Now suddenly, suppose in a substation a transformer gets burnt. If this is a big substation, then a outage of a transformer can cause a outage to a section of consumers, right? So any failure actually leads to blackout in a portion of your network. So when there is blackout, that means you are unable to sell your electricity, right? So you are not getting a revenue. So it is very important, especially in smart grid scenario where utilities are basically private utilities, right? They have to earn their money to run their system. So it is very important that you reduce your outage time. To do that, what you need is you need to predict the failure so that your outage is minimized and to prevent it from failing. So for this, various kinds of health monitoring has become popular, especially the health monitoring of transformer. So if you know your transformer health is deteriorating, you can plan ahead the necessary step to either replace the transformer or prevent the failure. So various automated techniques or automated measurement or monitoring process are being considered in future smart grid. Okay, right. So another thing is PMUs are deployed widely, right, for stability monitoring of power grid, right? Because PMUs gives synchronized measurements, right? So now you can measure the phase angles directly, right? It helps you in the monitoring of power systems, right? And also you can monitor the oscillations more accurately, correct? Any fault, any failure which is happening, especially whenever any blackout happen, it happen in stages. Like your system slowly goes into blackout stage, like multiple faults happen and slowly your system degrade and your system finally goes to blackout. So usually the system operators have some amount of time to react to stop the blackout. So in these cases, devices such as PMU plays a huge role. So this device give you more accurate picture what is going on in your grid. So you can take necessary action to stop the blackout or any cascaded failure. Another important smart grid feature is self-healing, right? So what you do is you operate power grid in a connected mode, but you identify small autonomous islands, right? That means in case any disturbance happen in a particular area, then you can isolate that area and the remaining system can continue to work. So we call it control island basically. So you should plan or operate in power system in such a way that if there is a fault or anything, your system can self-heal. Okay. This the main purpose is to ensure that your any failure does not propagate too much, like your any disturbance in contained within a region, right? So other region remain unaffected. Now, due to use of digital devices, now security has become a huge issue, right? Now, smart meters, they are nothing but digital device, right? Now, they have become attractive targets for hackers, right? So they can hack into your smart meter and fabricate your energy meter readings, right? They can also access your the AMI infrastructure of utilities, and they can mislead the utility to make incorrect decisions about local and regional usage capacity. Right? Similarly, another aspect is privacy. So smart meters actually records your daily activity, right? When suppose when the in the morning when you get up, you prepare for your office, right? You switch on particular loads, right? And when you leave for the office, you switch off your electric load. Again, when you come back from office, again you switch on. So here you can see that the house occupancy status, what kind of loads you are using, all this gets recorded in your smart meters. That means your privacy is there, right, in the smart meter readings. So someone can steal this information and get your private behavior. And then if they are, suppose they are a thieves, so from the data they can understand that you are not there, maybe you went for holiday, right? So they can access your smart meter and get that information about your activity, and they can plan their criminal activity based on your information which is recorded in smart meter, right? So similarly, at transmission level, at system operator level, this is a much bigger issue. Like suppose a control center which is monitoring power situation in a region. Suppose take Southern Regional Load Dispatch Center. So they basically have a control room, and in the display, all measurements from whole southern region getting displayed. Now, if some hacker can access your data and manipulate the data, like false data injection, then the operator will see something different scenario, right, than the reality. So he may take a wrong decision based on the fabricated data, right? So this has become a huge concern in case of smart grid. Actually, we know that we had a attack in 2020 in Mumbai. Like several power utilities like Tata Power, other utilities, they were subject to this cyber attack. And because of the attack, there was a huge power shutdown in the whole system in Mumbai, right? So this has become a huge problem, especially in the monitoring and the measurement aspect of control centers. So often the attackers, they try to block or delay the availability of your network, right? They will push lot of unnecessary data packets in your network so that your network become overwhelmed, and as a result the legitimate data cannot pass through your network. Another is data integrity attack. So attackers can deliberately modify or corrupt the information shared within the smart grid. So we will basically see something different than the reality. Okay. And information privacy, like because your private information, your account number, electricity usage, all this information is there stored with the utility. So attacker may try to get this private information from the utility. So cyber attack in power system is basically a reality. Okay. So every area, substations, transmission level, generation, they are being subjected to cyber attacks. Right? Now, cyber attackers can be of various types. Like there can be hackers, there are even insiders. Like if an employee is not happy, is angry with their employer, right? They can try to damage by doing some attack. Right? Similarly, nations. So cyber warfare has become popular. Like so, nations are targeting other nation through cyber attacks, right? Then you have phishers, spammers, malware, criminal groups, botnet operators. So there are many, actually many entities who are attacking your cyber network, smart grid, right? And the impact of cyber attack can be devastating. Like consumers can face financial loss, identity theft, even blackmail, interrupted service. right? Then companies, obviously business disruption, customer loss, information loss, financial loss, intellectual property loss, right? Power grids, blackouts is much more dangerous actually. Demand supply gaps, cascade failure, delayed or blocked meter reading. Actually, in 2015 and 16, there were huge successful cyber attacks in Ukraine, right? And huge number of customers lost power for very long time due to the successful cyber attack. So to stop the cyber attack, what you need from grid side is basically access control, authentication, attack detection. You have to take countermeasures, right? Network protocols, security. Similarly, from government side, coordination with industry, you have to develop research for efficient infrastructure and protection tools. Okay. Policy is very important that because technologies may be there, but you have to impose the technologies via policy, right? So policy level uh, work is very important from the government side to address cyber security in smart grids. Okay. So now the last topic what we have started working. So I thought briefly I will discuss it. It is basically data markets or smart grids. So we know, right? So we have more digital device and they are generating huge amount of data, right? So it's like smart meters, SCADA, disturbance recorder, phasor measurement unit, weather sensors. So if you just calculate that how much data is getting generated just by 1 million smart meter installed, just the smart meter. So you can see that how much data is basically getting generated. It's a huge, huge amount of data, right? So here one per day means one data cent per day. One per hour means one data cent per hour. So you can see that if the smart meter sends 15 minutes, one data in every 15 minutes, then 2920 terabyte of data will be generated by just 1 million smart meters, right? So now you can imagine a country like India, only smart meters, how much data will be generated, right? And in addition, you have other sensors such as PMU, SCADA. So you can understand enormous amounts of data gets generated. Now, currently, all these data mostly stay with the utility, and we all know, right, how much it is difficult to get the data from the utility, right? Now, from utility perspective, they also like don't they are not because they don't have any benefit like giving the data to you. It is their property. So we want the data, but they think why they should give the data. Right? As a result, these all these generated data they mostly stay with the owner. So currently there is a lack of exchange platform. Right? So we proposed the data market for monetization and exchange of smart grid data. Right? So what is data market? It is a online platform similar to your Amazon, Flipkart, right? So your data sellers, which are basically utilities, they will register themselves and they will register their products, which are basically data, right? And whoever wants to buy, like, but you have to regulate who can be buyers, whoever, so they can log into the website and buy this data. Okay. So now if we look at the products in data products, like what can be sold in smart grid data markets. So it can be parameters of power system elements, measurements from smart meters, SCADA, PMUs, power quality meters, disturbance recorders. In addition, all planning data, network generation expansion data, then operating data, scheduling, congestion can be sold. In addition, various standards on smart grid, which are usually sold separately, that can also be sold via data market. Then energy market related data, meteorological data, GIS data, so those can be sold. Now, apart from data, other products which are related to data, such as data analysis tools, right? Because often after buying the data, you need some algorithms to search, clean, and filter and process your data, right? So you need some data analysis tools also, right? In addition, you may need some software for forecasting your various parameters, right? So data analysis tools like various softwares, right, related to data analysis can also be sold via data market. Then we also have consultation services. Like there are many consulting companies, right? So they can offer their service to analyze the smart grid data and give some meaningful result to the customers. Right? So possible participants in smart grid data market can be data producers, service providers, application developers, data consumers, and owners of smart grid. So here owner means that online platform. There will be some company, right, who will be owning that data market. Similarly, in case of energy market, we have Energy Exchange of India, right, IAS, Power Exchange of India, PXI. So similarly, the data market will also be owned by somebody, right? So they are the owners of that platform, right? So data consumers will basically buy the data, okay, and then application developers will be the people who will develop various application for to analyze these data, right? So various softwares basically they will be developing. Then you have service providers. So it's like a various companies who will provide service. So they will basically buy various softwares, and using those software they will provide solution. And data producer are nothing but power generation companies, transmission companies, system operators, right? Industrial companies, consumers, meteorological departments, energy market owners. Okay. So this we have discussed. Now, if you say that, what will be the advantage of smart grid data market? So, first of all, you can generate revenue. This is a alternate or another way of generating revenue, especially when our distribution utilities are running into losses, right? So, for them, this can be another way of generating revenue, right? Used by selling the data. Now, currently, the data once like after the online monitoring, the data are stored either in CD or in some drive, because utilities don't have much after use of this data, right? Now, if utilities know that they can earn money by selling this data, it will encourage them to store it better way. So better data management practice will be there if data market comes. Data accessibility. This is very important, right? Because even though we want, we don't have the way to access the data, right? So like any market, data market will also be a fair medium to access the data. So impact on energy market. So in energy market, so many entities, they place bidding, right, to buy and sell data. So now if you have more information about power system available, so you can, the companies, the participants in energy market can make better bidding, right? So your whole system can become more efficient. Then obviously you have important like uh, improvement in power system operation, planning, analysis of blackouts, benefit to equipment manufacturer. This is another important thing. So if you look at currently the manufacturer, they often do not have access to real-time data. So what they do is they manufacture or design their equipments in a very pessimistic way, right? And often using simulated data, right? Like in a protection, suppose some company is developing this power swing blocking technique. So they will probably use some software to generate some data and use it to test their equipment or relays. But if real-time data is available, so these companies can improve their equipments by using the real data, right? And obviously, we have benefits to academic researchers who often look for data, but they don't get the data. Okay. So one main approach, one main problem in data market is basically how to price the data. Like what will be the cost of data? This is, we don't have much knowledge about it, right? So there can be many pricing attributes, like what is the object of pricing? Do you want to make some profit, or do you want to just recover my cost, right? Similarly, impact of data. If the data has more impact, more usefulness, the data can be priced higher. Another thing is cost of metering infrastructure. So the infrastructure through which the data got generated, if that infrastructure cost is higher, then data should also be higher. As an example, PMU infrastructure is costly. So the data which is coming out of PMU is should be also costly. Then age of data. If the data belongs to 5 years ago, then it may not have much application today. So the recent data should have higher price with respect to old data. Then again volume. So if I get more data, I pay more. Right? Duration of access. If I have data for longer time duration, I pay more. Accurate data, again I pay more. Right? So database errors. If the database contains lot of errors, missing data like that, so I should pay less, right? So this will actually encourage the utilities to maintain their data better. So data collection cost. So if there was cost associated with the collection of data, then we should incorporate that in the price data pricing. So arbitrage free data pricing is nothing but arbitrage means that whatever price is set for the data, I should not be able to get the same data with lower price. Okay. That is called arbitrage free pricing. Okay. So that's all. I think, yeah. So smart grid is a very big concept. A lot of things are happening. So I just tried to just give you some overview of this whole smart grid area and some important aspect I have tried to touch. So now I am free to take any questions if you have any.
Yeah, so thank you, Dr. Sarasij Das, for the comprehensive and overall overview of the smart grids. So it's time for question answers and discussion time. So if any of the participants would like to do, uh, yeah. So Saroj Khan Singh.
Yes, sir. Thank you, sir, for your nice presentation and throwing light. So you mentioned about pricing. So a related area would be valuation. So could you throw some light on that, because most of the IT companies and engineering companies like one I work at have a lot of intellectual property. So data would be something of that nature. So how to value these kind of companies who deal with mainly this data?
Yeah, so data pricing and related area is actually is a very new. So practically there is not much literature available that how to price the data. Okay, so we have just started working on this topic. So at this moment, I would say that solutions are not available. We have to come up with solution.
Thank you, sir.
Any other questions from any participants?
Good afternoon, sir. I have one question
Yeah.
related to system integrity protection, sir. Because in smart grid nowadays, since all phasor measurement units and all sensors are being used, so what could be the possible orientation for SIPs, sir?
Uh, Possible orientation mean what? Like what exactly?
Means what could be the research direction for SIPs? Because I was going through certain papers, they were majorly focusing on changing the characteristic of distance relays and all. So can you throw some light could of the possible directions
See, one
on
major
which?
thing in future is to handle the renewable intermittency. So suppose your wind or solar generation has dropped suddenly, and there is a huge load generation imbalance in the system. So your system integrity protection should immediately come into picture, and based on the scenario, it can shed the load shedding, shed it, but some amount of load. So handling the renewable intermittency can be one research area for SIPs. And apart from that, another thing is outage detection or cascading outage. So because that has again become an issue, because now power system has so much complexity, like intermittency of renewables, loads, economic pressure. So power system is often being operated at the limit. So research should be done to develop SIPs which can detect the possible outages and take necessary action to stop the blackouts, cascading outage basically.
Thank you so much, sir.
Any more questions?
Jagdish, I can see. Jagdish.
Uh, Jagdish, if you have a question, you can unmute yourself and ask.
Hello. Yes, sir. Ac- Hello.
Yeah,
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 yeah.
we can.
Yes, sir. As far as security of smart grid and data security is concerned, sir, which lightweight cryptography technique is best suited for this smart grid security in present scenario?
See, now it depends on what data you are securing. Suppose you are securing the historical data, so you can use some cryptographic technique like RSA and those kind of techniques. Now, if you are trying to secure real-time data where you don't have much delay, so their cryptography technique may not be much suitable. Even lightweight also may not be much suitable. So there it is subject of research. So we also tried to work on something called steganography. Steganography is a lightweight form
Okay.
of data protection, so which is much lighter than cryptography. Okay, so this is, I would say that this is an open area, that how we can um, secure data in IC 61850 standard or synchrophasor communication, where time delay is very important. So yeah, cryptography cannot be a solution there.
Sir, I am also working on this smart grid project, but sir, the main problem I have seen that during the key exchange problem, uh, is you are you think that RSA is a better technique for the key exchange, or something else we have to adopt?
The RSAB is popularly used. Okay,
Okay.
so that is more popular, but I would not say that whether that is the best or worst, but it is popularly used. Yeah, definitely.
Okay, sir. Sir, one last question, sir. I want to ask that can something be done? So, for example, AES is a heavyweight. There is some that can be done to make the lightweight version of that AES, which can fit into this scenario? Do you think so? It can happen. It can.
So
Possibility is.
So this is subject to research. So there are efforts to come up with lightweight cryptographic algorithm. There are this constant efforts, especially IoT applications, right? So there are efforts, but I'm not sure whether any algorithm has been commercialized yet on lightweight side. Yeah.
Okay, sir. Thank you for such a nice presentation and answering my queries. And I am thankful to you. Thank you, sir. Thank you.
Okay. Okay. Thank you.
Thank you, Jagdish. Any more questions? Okay, so there are no more questions, so we'll wind up this particular session. So, on behalf of the department as well as all present in this program, I would like to thank Dr. Sarasij Das for spending time with us and sharing this valuable knowledge. And the recordings of the session will be provided to the participants so that they can listen to these sessions later and they can have more understanding on these topics. So thank you everyone. Thank you all for joining. So the next session will be at 2:30 in the afternoon. Dr. Anubama Kohli from IIT Bombay will be joining us for that particular session.
Thank
Okay.
you.
So,
Thank you very
thank you.
much.
Thank you. Thank you. Okay. So see you at 2:30, same link.